You guys can see like just the lecture and nothing else, right? Okay, I'll take that as a yes. Let me send the stuff into the big channel. There's a lecture notes if you want to. If you want to.
Oh wait, I think states actually goes pretty well with expected value, right?
Yeah.
Like there's a lot of overlap. Nice. This is a complete coincidence.
Yeah, I didn't know that Ethan was gonna lecture on expected value. So first of all, let me just make like a few clarifications. Well, make sure to join the Discord. I assume you have, and if you have, then if you look at the big channel, then there is a copy of the lecture notes that you can follow. I'll post another copy once I'm done with all these edits that I'm gonna make, because this is not a full, like, not everything is in there, as you can see. Wait, oh shoot. Okay, I already have all the stuff written out here for some reason. Let me pull up the other copy. Sorry. Actually, no, that was the right copy the whole time. So, okay, I'll just reshare it. Here we go. Okay, so you guys can see me scroll through it, right? Like, I'm just making sure. Okay, well, first of all, states is a strategy for solving types of combinatorics problems that are usually otherwise like very difficult to solve. These problems occur quite often on late AMC 10 or 12, as well as mid to late AME. That's just like the where it's found. The main gist is setting certain outcomes that happen during a problem statement as different states. This is used when we have situations that change during a problem, but always retain one of a few specific configurations. So I'll start with an easier example so you can understand what I mean by saying this. So this is just from the AMC 8. A cricket randomly hops between 4 leaves on each turn, hopping to one of the other 3 leaves with equal probability. After 4 hops, what is the probability that the cricket has returned to the leaf where it has started? So this is not an expected value problem like some other ones we're going to go through. And there are plenty of other ways to solve this problem. You can do casework. I believe there's only like 2 or 3 cases that you need to consider anyway. However, we're going to solve it with states because this provides a good introductory example. So we first defined P of n and W of n as the probabilities of not being on the original leaf and being on the original leaf after n hops. So basically P0 is equal to 0 and W0 is equal to 1 since we're starting on our original leaf, and then we can't start on a different leaf. So we then form equations. These equations, actually, we should get to them later. I'll go with the diagram first. This is probably easier to understand. So here are our 4 paths. We have W, P, P, P. W is the original leaf. And when you're on W, the next hop has to go to one of the 3 P's. We can group these into like one kind of box. So all three of these P's are symmetrical because they're the same case. Like no matter whether the frog goes to this P or this P or this P, it's still not going to be on W, and it still has the same chance of going back to W, which is 1/3. And if you're on P, then there's a 2/3 chance that you stay on the P's, because if you're starting at this P, for example, there's 1/3 chance of going here, 1/3 chance of going here, 1/3 chance of going here. So these equations are basically like they're the most fundamental parts of states problems because these are how you solve for your answer. And these equations are always derived from our diagrams. Sometimes you don't need diagrams, but I always do them because it's definitely very helpful. So Pn plus 1 is equal to 2/3 Pn plus Wn. And this equation, what it means is that the probability that we're on W after n jumps is Wn. And that directly contributes to P of n plus 1, because if you're on W at time n, then you're always going to be at P on time n plus 1. And then 2/3 Pn comes from the fact that if you're the probability, if we're on P of n, then we go to n plus 1 with probability 2/3. So if the probability we're on a P is P of n, then that 2/3 of that probability is added to P of n plus 1. And then likewise, we have 1/3 Pn is equal to Wn plus 1, because you can't go from W to W. And if you're on P, you have a 1/3 chance of going to W. And then now, once we have these equations, the problem is reduced to simple calculation. And I'm going to do it here, I guess. So if you substitute, so if we're solving for W and plus 1, it's just easier to just draw a table, since we only have four. We only have up to n equals 4 to calculate, is what I mean. If you were doing the AME in 1985, which you were probably not alive for, you would have seen the same problem, but worded differently and with 7 steps. So if we have P, W, N, 1, 2, 3, 4. So our W is 0 for 1, and then our P is 1. The reason why is because at time equals 1, it must have moved from W to P, since it started on W. And then for 2, we have W is equal to 1/3. Sorry. And then this is 2/3. And you don't even need to calculate the P, because we know that the probability of P and the probability of W add to 1. So we can just write 2/3 here. Then we have 2/9 and 7/9. Oh, this is not great. And then 7/27, and that's our answer. So we'll move on to harder expected value problems. These are the ones that are like most common. So they're approached in a very similar manner to the AMC problem we did, and are often actually quite intuitive if you know how to do it. So an ant and an anteater they're on opposite corners of an octahedron, two connected square pyramids. It looks kind of like this. The ant starts at the top of the first pyramid, and the anteater starts at the bottom of the second pyramid. So they start on opposite vertices. I didn't want to say opposite because it might confuse people, but they're basically on opposite vertices. Both of them travel about 1 side per second, and all sides of the octahedron are the same length. Whenever the ant and anteater reach a new vertex, the ant picks a random vertex to head towards. So if this ant starts here, then it could head over here, over here, over here, or over here. And the anteater just picks the closest path using the edges of the ant. And since the anteater is here, ant's here, all these paths are the same, like in terms of distance to the ant, which means the anteater, at least for turn number 1, will also go to a random vertex. What is the expected value what is the expected time before the ant and anteater meet? And I'll refer to this as the ant dying. I mean, you can kind of infer that the ant will die if it meets the anteater. The key to understanding this problem, as you may figure out independently, but more likely to figure out when you make this diagram itself, because the diagrams are obviously the most, they're very, very important, is that there are only 2 states. The one is here. Oh, no, that's not one. One is here. One is the ant and anteater are separated by 1 vertex, or 2, they're on opposite vertices. And there are no other states besides maybe you could count them being on the same vertex as a state, but I don't really want to do that, because it's basically the quote-unquote 0 state. The expected time is 0. So the latter means that the anteater will move at random along with the ant, and the former means that the anteater will take the shortest path toward the ant. There's only one way, and it's this way. So we can begin by playing around with the 2 states. So let's start with 1. 1 is probably easier. We know where the anteater is going to move already. So where's the ant go? Well, the ant has 4 choices. It can go back this way, which means that they will cross here. If they cross, they die. So that's RIP here. The ant can also go to this vertex, or it can go back to this vertex, or it can go to this vertex. If it helps, you can number the vertices as well. I didn't do this for this problem, but I did for the homework problem, which is, spoiler, very similar. So that means it has a 1/4 chance of dying and a 3/4 chance of surviving. And if it survives, then it'll always be 1 away because the ant moved to a vertex that's 1 away, and the anteater is at where the ant used to be. So it's still going to be 1 away. So we represent that here. 1 away has a 3/4 chance of returning to 1 away and a 1/4 chance of going to dead. And when I say dead in 1/2, it means it's dead in 1/2 seconds. And that's a very important distinction to make because it's not dead after 1 second. It's dead after 1/2 since they both meet in the middle here. Now, if we have our anteater on the opposite vertex of the ant, then the ant moves at random. And since the octahedron is symmetrical, then it actually, like, we can just say that the ant will move here. Like, this is just our without loss of generality. And the anteater has 4 options. It doesn't know which way the ant's going, so it's not gonna, like, quote unquote predict. It can go to this vertex, that vertex, or this vertex. And there's a 1/4 chance that they meet here, and that's a dead. And then there's a 1/4 chance, a 1/2 chance that it goes to one of the vertices next to this, so the 2 will go to the 1 state. So the 2 state will, like, move to the 1 state. And then there's a 1/2 chance, a 1/4 chance that the anteater goes to the opposite vertex as the ant, which means that it'll stay at the 2. We represent that here. With 2 away, it goes to 1 away with 1/2 chance, stays at 2 away with 1/4 chance, and goes to dead in 1. Dead in 1 means dead in 1 second, and that has a 1/4 chance. So these diagrams are also known as Markov chains. Not that it really matters, but it's a cool thing to flex, like it's like a cool name, you know. So another key insight that this is that the state will never change from 1 to 2. You'll see that just by doing the diagram. You can also see that by doing this diagram. If I was solving this problem, I'd do both, just saying. So time to denote variables again. This time we use expected values, so I just call the variables E1 and so on. You can do whatever you want with variables, but this is the easiest for me to understand. So E1 denotes the expected lifespan of the ant when it is 1 square away from the anteater. Denote E0 and E2 similarly. So E0 I shouldn't have added here, honestly, because it's a little bit confusing, because it's pretty much just 0 anyway. So E0 just basically means you're dead. So it helps, yeah. Actually, I did include it for a reason, and that's because it helps visualize the fact that the sum of the probabilities adds to 1. And that's maybe a consolation for you, because, like, it's good to make sure that the probabilities add up to 1, because if they don't, then you've done something wrong. So we use the diagram to create our equations. E1 is equal to 3/4 E1 plus 1/4 E0 plus 7/8. E2 is equal to 1/4 E2 plus 1/2 E1 plus 1/4 E0 plus 1. This is just a restatement of this. The only weird thing here is that you have our 7/8. Why is it not 1 here? So this 1 for E2 means that 1 second is always passed. So if the ant dies, or if the ant goes to a different vertex and survives, 1 second is going to pass, like, before the next state. Whereas in the E1, there's a 1/4 chance that 1 second doesn't pass because it dies in 1/2 instead of 1 second. So there's a 3/4 chance times 1 that 1 second passes, which means, quote unquote, like, if it survives, then 1 second passes. Then there's a 1/4 chance that 1/2 second passes. And it's 1/2 seconds because it's dead in 1/2, and the state changes after 1/2 seconds. So we simplify the equations, get rid of the E0s, and then this is easy to solve. E1 is equal to 3/4 E1 plus 7/8, which means it's just 7/2. E2 is equal to 1/4 E1/2 plus 1/2 E1 plus 1. And since we know E1 is 7/2, then we get 11/3 as our answer. It's good to make sure that your answer is reasonable. Let's say, for example, in this problem, we got an answer of less than 1. Then you can reason, oh, well, that's just bogus, because it's obviously going to be more than 1. So let's go to problem 3. This is, in my opinion, the hardest problem on this handout. Let A1, A2, A3, ... A12 be a dodecagon. 3 frogs initially said A4, A8, and A12. At the end of each minute, simultaneously, each of the 3 frogs jumps to one of the 2 vertices adjacent to its current position, chosen randomly and independently, with both choices being equally likely. All 3 frogs stop jumping as soon as 2 frogs arrive at the same vertex at the same time. The expected number of minutes until a frog stops jumping is m over n, where m and n are relatively prime positive integers. Find m plus n. So what gives away that this problem involves states? Well, first let's see what happens when you try to bash it. So we have 4, 8, and 12. And then we'll be like, okay, well, maybe these 4 and 8 will meet. What's the probability that this happens like as soon as possible, which is after two times? And that is going to be 1/16, right? Because you have the 4 moving to 5, 8 moving to 7, and then they both have to move to 6. So there's 1/16 times 2, and then maybe multiply by 3 to count for the fact that there are 3 pairs. And then you realize that you have to do it infinitely, and that there's tons of different possibilities for you to consider. And also that like it's not a given, it's not a guarantee that it's going to be easily represented by a geometric series. So, I mean, you realize that, oh, look, these frogs are symmetrical. They're at 4, 8, and 12. They're all the same frogs. Like there's no distinction. It's not like one of the frogs is red and it makes a difference. So symmetry is the big key. I wrote it up at the top here. Symmetry. I didn't really mention it when I went through this part, but symmetry is the biggest key that we should be using states, and not having symmetry is the biggest key that we should not be using states. So the symmetry here is that all the frogs are the same. It's also that the 4, 8, 12 don't really matter. The reason why is because it's a circle. By a circle, I mean the decagon, but it's kind of a circle because it's cyclic. And it's not like once you get to 1, you have to go to 2, because you can go from 1 to 12. So now we start using states to it. We assign a number 1 to 12 to each of the vertices. 1, blah, blah, 12. And we should set states, right? And then, so at first you're thinking, oh, well, there's 12 choose 3 different ways to set states, right? Or technically, it's not 12 choose 3 since all the frogs have the same parity, but it's still a lot of different states for you to consider. And so instead of just making the states based off of which vertex these frogs are at, we can make them based off of the distances between each frog. Because 4, 8, and 12, the problem answer would be the exact same if it was 3, 7, and 11. It would be the exact same if it was 2, 6, 10. And it makes sense, like, because it's the same thing as just shifting all the frogs. So after you realize that the distance between the 3 frogs always has to add up to 12, right? 8 minus 4 is 4, 12 minus 8 is 4, and then 4 minus 12 is 12. 4 minus 12 is 4, because the distance is 4, and those add to 12, and they're always going to add to 12. For example, if the 4 moves to 5 and the 12 moves to 11 and the 8 moves to 9, then you have 5 to 9 is 4, 9 to 11 is 2, 11 to 5 is 6, and those add up to 12. So they all add up to 12, and the distances are always all even due to parity, and that's kind of easy to notice as well. We can set states as the distances between the 3 frogs, and states usually, like, I've never seen a states problem that involves more than, I want to say, 4 different states, because that, like, when you have 4 different states, then you end up sometimes with a system of 4 equations, which is kind of annoying to solve. So there's only going to be a spoiler. There's only 3 states for this, but the starting position is going to be 4, 4, 4. And if we look at the 4, 4, 4, it can stay at 4, 4, 4 if all 3 frogs move left, or if all 3 frogs move right. And there's a 1/4 probability for this, because it's 2 over 8. So there's a 1/4 chance that it stays at 4, 4, 4. What if it doesn't stay at 4, 4, 4? Well, if you test it, then you'll notice that due to symmetry, it becomes 2, 4, 6 in some order. So it can be 2, 4, 6, 6, 4, 2, 4, 6, 2, 4, 2, 6, 6, 2, 4, 2, 6, 4. And it doesn't really matter what order they're in, because again, all the frogs are symmetry. They're all symmetrical. So 2, 4, 6 is the same. This essentially the same thing as having 4, 2, 6 with regard to expected value. So since all three frogs are essentially the same, we don't worry about order. So now we consider the 2, 4, 6 state, and this is a little bit more complicated, so I'll outline all the possibilities. So without loss of generality, the frogs are at positions 1 through 7. The 8 possible places for them to go are 0, 2, 6, 0, 2, 8, 0, 4, 6, 0, 4, 8, 2, 2, 6, 2, 2, 8, 2, 4, 6, 2, 4, 8. And then I wrote out which state these correspond to. For example, 0, 2, 8 corresponds to 2, 4, 6 because there's a distance of 2 between 0 and 2, distance of 6 between 2 and 8, and a distance of 4 between 8 and 0. And then sometimes we have something like this, 2, 2, 6 or 2, 2, 8, which is finished. And by finished, I mean the frogs will stop jumping because 2 frogs have arrived at the same vertex. So I just wrote out all these states. There's also a special one, 2, 2, 8 state that we haven't mentioned yet. So 2, 2, 8 state, I have calculated the probability for that, but if you want, you can do that as an exercise. I'm not going to go over it during the lecture. So I've written out all of these diagram here. 4, 4, 4 is a 3/4 chance of going to 2, 4, 6, and it has a 1/4 chance of returning to 4, 4, 4. 2, 4, 6 is a 1/8 chance of going to 4, 4, 4, a 1/2 chance of returning to itself, 1/4 chance of finishing, and a 1/8 chance of going to 2, 2, 8. And a 2, 2, 8 has a 1/4 chance of going to 2, 4, 6, a 1/4 chance of returning, and a 1/2 chance of finishing. So now we can express this diagram as a system of equations. So E246 represents the expected value from the 246 state, and similar meanings apply to the other E values. So E444 is the expected value from the 44 state to finished. So like how much time does it take to be done, essentially. And then the 228 state is the same thing. And then we have our equations. The 0 is our done. And don't forget to add 1 to all these. The reason why you have to add 1 is because 1 second passes in between the next state. So you can verify that pretty easily. Like with a, like let's say a sample problem is like there's a 1/2 chance of returning to itself and a 1/2 chance of finishing. There's only 1 state. Then you realize that if you don't add 1 to the question, then it's going to end up being 0. And the reason why is because you get the equation x is equal to 1/2 x. And then plus 0, because 0 is when you're done. And that obviously doesn't work. So you have to add 1. And then if you have x equals x over 2 plus 1, then it's easy to solve that problem, x equals 2. So once we have our 3 equations here, the solution is clear. By clear, I mean you have to solve a system of 3 equations, which I'm not going to do because I'm lazy and I don't have that much time. And then we should know which variable represents our solution. It is E444, since the frogs start in a 444 position for 8 and 12. Okay, so the last problem is going to be called blending states with insights. What this means is just like creative problems that are slightly different from this kind of thing. That is just computation heavy. Roshan, Sylvia, and Ted play the following game. Each starts with $1. A bell rings every 15 seconds, at which time each of the players who currently have money simultaneously chooses one of the other 2 players independently at random and gives $1 to each player, to that player. So let's RST. Let's say they all start with 1. Let's say Roshan gives his money to Sylvia. Ted gives his money to Sylvia. Sylvia gives her money to Ted. So R is left with 0. S now has 2. And T now has 1. Now let's say in the next turn, Sylvia and Ted just give each other their money back. Then it's the same thing. And Roshan can't do anything. It's not like he gives money to anyone because he doesn't have any money. So this happens every time the bell rings. And what is the probability that after the bell has rung 2019 times, each player will have $1? So this problem is a little bit easier, and by easier I mean computationally, and that's because we only have 2 states to consider, the 0, 1, 2 state and the 1, 1, 1 state. You can test that. So I mean, let me just like make it kind of clear here. So the sum of all the dollars in circulation is 3, and it's impossible to have 300, which leaves us with only these 2 states. It's impossible to have 300 because Sylvia has to give her money to someone, essentially. So she'll never be able to get $3 because one of the dollars is always moving from Sylvia to someone else. And then it's impossible for someone like Roshan to have $3 because he can only receive 2 when he has 0. So we then construct another diagram. 3/4 chance of returning to itself when you have 0, 1, 2. It's either when these two give the money to each other, or Sylvia gives her money to Roshan and Ted gives his money to Sylvia, because then R has 1, S has 2, and T has 0, so it's still 1, 2, 0. And then there's a 1/4 chance of going to 1, 1, 1. And this only happens when Sylvia gives her money to Roshan. Wait, no, Sylvia gives her money to Ted, and Ted gives his money to Roshan, because then it's 1, 1, 1. Now, the 1, 1, 1 chance has a 1/4 chance of returning to itself. Either they do like a cycle like this, or they do a cycle like that. And then that's just 2 ways out of 8. The rest are like quote unquote symmetric. And then there's a 1/4 and then the 3/4 chance, which is the rest of going to the 0-2-1 case, 0-2. And you might be realizing, oh, now that we've made our diagram, where do we go now? Because 2019 is a lot. Like, that's a big number. If this was 2019, we'd be screwed, because then I'd have to compute, like, oh, what is 1 minus 7, 27? Oh, 20 over 27. And then divide by 3 again, 20 over 81. And then it's going to be some really whack number over, like, 3 to the 2019, or 2018. Except then you realize, oh, well, it doesn't actually matter any of the other states, because there's always a 1/4 chance of going to 1, 1, 1. No matter what state you're at after 2018 bells, there's always going to be a 1/4 chance of going to 1, 1, 1, which means their answer is just 1/4. If the question was asking for after 1 bell, after 5 bells, after a million bells, it doesn't matter. It's still the same answer. So we're at the end. Perfect timing. Problem 5. I can stay and do this one if you guys want, because it's not in the video. Problem 6 is in the video, and it is the same as problem 2, but if the and has a movement, like, there's 2 parts to it. A is the and has 2, and B is the anteater has 2, like, as in terms of how fast they are, which makes this a little bit more complicated, and that's simply because there are just more ways that the 2 animals can move. Problem 5 is finding another solution for problem 1. And this problem, it approaches the problem using the states of only 2 of the frogs, as all 3 cannot meet at the same vertex. And you guys can do this one for homework. What I will do, though, before I leave, is I will put you on the right track by proving that all 3 cannot meet at the same vertex. And this is quite easy. Let's say they all meet, like, without loss of generality, they all meet at vertex 1. The only 2 ways to get to vertex 1 are through 12 and through 2. Since we have 3 frogs, by pigeonhole, there has to be 2 in the same vertex that turn before, and that means they would have stopped already. So that's it. I guess, hope you enjoyed the lecture. You can feel free to go.